Hi, so today we are going to discuss how to figure out where to shade for linear inequalities. The traditional method for doing that has been using test points. Okay, so I'll start by example just to remind you of what that method is. So for example, let's say we are given the inequality y less than or equal to x. We would first draw that as an equation, which would look something like this, going through the origin, and then we would choose a point on either side of the inequality and see if it's true. If it's true, then we know that that inequality is satisfied and is indeed in effect. That point that you choose cannot fall on the line. Okay, it has to fall on either side of the line. So let's say we choose the point -2, 5. So -2, 5. If you plug that in, you get that the y value is 5. 5 is less than or equal to -2. -5 is not less than or equal to -2. That is a false statement. So therefore, we know that point does not satisfy the inequality. So that means we're going to be shading on the other side of this line. Okay? Now that is the testing point method. Okay? Now in this video, I'm not going to be doing going over the intuition or why it's true or any proof or anything like that. But I will explain the method and what you should be taking from it, what the conclusions are. So this is the testing point method. So the test point method. Okay, so you just plug in a point that's not on that line, and if it satisfies that inequality, then you shade on that side. If it doesn't, you shade on the other side. Now, some people will say, well, why do you need another method? Why don't you just plug it in? Well, sometimes these equations are hideous. Okay, sometimes you do not want to be doing, all these complicated computations, right? So if the coefficients in your linear inequality, if those coefficients are irrational, or if you have a lot of fractions and you don't want to keep dealing with all these fractions and things like that. If the computation is messy, you don't want to have to keep plugging in these points. And in fact, when you are dealing with systems of inequalities, you're going to be having to plug in multiple points into multiple different things. You kind of don't want to have to do that. So the method I'm going to show you in this video is going to be an easier way of determining where you shade by just looking at the equation. You don't have to plug anything in. You just have to look at the equation and make sure it's written in a certain form. Okay, so that method is called the gradient vector method. Okay, and the gradient vector method basically says this. Okay, it says that if the corresponding linear equation is written in standard form, under certain conditions, and I'm going to explain to you what that, it's really one condition, what that condition is. So under certain conditions, then the gradient vector will point in the direction of increasing value. And I'm going to explain what that means. Increasing the direction of increasing value. Okay? So let's dive into that. Okay? I'm going to do this by example because I think that's the easiest way to deal with this rather than giving you all this theory and trying to create notation and all those different things. Let's just do this by example. So, for our first example, let's just take the inequality 2x minus 4y equals the inequality. So let's take this less than or equal to 8. Well, let's just take. Matter of fact, I'm not going to make this inequality. I'm going to just deal with the equation. It's easier to do that than to deal with the equation. So let's just deal with the equation. So I have the equation 2x minus 4y is equal to 8. Okay? Now, first thing I want to do is I'm going to actually graph this so you can see visually what's going on. Did my picture go away? Here it is. So I'm going to do this by intercept. So if you do it by intercepts and you plug in 0, that means that the y value is going to be -2. So I have 0, -2. And then I have the other intercept is just being 4, 0. Okay, so this is our actual line. Okay, if I can draw it straight, it would look like a straighter line, but it's a line. And now that I have this line, I want to figure out, like I told you, how do I figure out where I need to shade? Okay, well, we're going to figure out what the gradient is. Okay, and the gradient, what the gradient vector is. And the gradient vector, simply enough, will just be the coefficients of the x and y term. That's it. Okay? Under the condition that the right-hand side is positive, it needs to be greater than 0. Your right-hand side needs to be greater than 0. Okay? So in this case, the right-hand side is indeed greater than 0. Okay? So our gradient vector is 2, -4. Okay? Now, if we go and plot 2, -4. So 2 units to the right on the x-axis, -4 units on the y-axis. So that's going to be in our fourth quadrant. So it's going to look like this. Okay, this is 2 minus 4. Okay? So now that we have the gradient vector drawn, what it tells us, okay, and that's what the method says, is that in that direction of that vector, the values of the expression are going to increase. And by expression, I'm talking about the left-hand side. I'm talking about 2x minus 4y. Think of that left-hand side as being one expression, and no, I don't want you to call right now, okay? Think about us having one expression, okay, and assigning that expression a value, okay? The value in this case would be 8 for that line, okay? Now, if you are on this in the direction of the gradient vector on the right-hand side of that line, then those values are going to be larger, okay? So that is, if I draw a value here, the value of that expression is going to be larger. So maybe that expression value is 9. Okay, and then if I draw another line here, okay, it's still to the right, maybe that value is 10, but it's also going to be greater than the previous line that I drew, right? So in that direction, the values are going to be increasing. So if I had an inequality that said 2x minus 4y is greater than or equal to 8, of course I know that I am going to shade on this green side. Right? Conversely, if I had an equation that said 2x minus 4y is less than or equal to 8. Well, if I'm less than or equal to 8, I can't be on this side. I have to be on the other side. I'm going to be on the blue side, right? So that's how we figure out where we need to shade, okay? By just looking at the coefficients on the x and y terms. And once we look at them, that tells us what the gradient vector is, and then we shade in the direction of the gradient vector, okay? So that's how we do it, okay? Now let's do an in-depth example, more of an applied example, where we're just taking it and we're applying it not to one inequality, though. We're going to be applying it to a system of inequalities. So let's take, for example, that we have this line, and this line. Matter of fact, let's see. Yeah. Trying to draw my line, guys. Yeah, that's good enough. It's not straight, but that's good enough. Okay, so let's call this line 1, this line 2, and this line 3. Okay, and let's say our feasible region is here. Okay, and I give you points. I'll tell you the vertices of the feasible region. So we have -5, -1, 1, 3, and 3, 2. Okay, so first of all, I need to figure out what each of these lines are. Okay, so first of all, I need to figure out the slope of each line, then I'll put it in point slope form. Now I'm going to assume as a prerequisite to this video that you already know how to find equations of lines, given that you know 2 points on that line. Okay, so I'm not going to take you through solving each of them individually. I'm just going to tell you what those equations will look like. So for line 1, that equation is going to be y minus 3 equals 2 over 3 times x minus 1. For the second equation, it's going to be y minus 2 equals 3/8 times x minus 3. And then for the third equation, it's going to be y minus 3 equals -1/2 x minus 1. So that's what you get when you take those points and you figure out what their equations are, right? You get the slope, you know a point on each line, you can put each of them in point slope form as I've done here. Now, once you do that, again, according to the method, we want to write them in standard form, okay, with the condition, however. The condition I'm going to make is that the right-hand side is positive, which you can always do. You can always make the right-hand side positive. So we're going to rewrite these equations such that the right-hand side is positive. And again, I'm going to assume that you know how to write in standard form, so I'm going to assume that as a prerequisite. Remember, standard form is where you have a coefficient times x plus another coefficient times y equal to some number. And that right-hand side number, I'm going to assume is going to be positive. So I'm going to write it out for you, but I'm not going to solve it directly here because I'm going to assume that you already know it. So this first equation turns into -2x plus 3y is equal to 7. The second equation turns into -3x plus 8y equal to 7. And the last equation turns into x plus 2y equal to 7. There's no specific reason that all of those numbers turned out to be, the right-hand sides turned out to be 7. That's just how it turned out, but that will not be true in general. Okay. Now, once we have written in the standard formula, we've made sure, again, that each of these right sides are positive, which they are, then we can figure out what our gradient vectors are. Okay, and as we did in the example previously, we know that our gradient vectors, like for this one, is going to be just what the coefficients are. So it's going to be -2, 3. For this one, it's going to be -3, 8. And for this one, it's going to be 1, 2. Okay, so we have our gradient vectors. All right, now we're going to go back to our picture. Okay, notice that, or I guess not notice that, but rather recall that our feasible region satisfy all the solutions in the feasible region satisfy the system of inequalities, right? So as if I choose any point in the feasible region, it just satisfies the inequality for line 1, should satisfy the inequality for line 2, and should satisfy the inequality for line 3. Okay? So that means that if I take any point in that feasible region, it should satisfy that line. And that should make sense to you. Okay? So keep that in mind. Now for the first line, I'm going to draw the first gradient vector. So the first gradient vector is -2, 3. So -2 on the x-axis, up 3 on the y-axis. So that's going to be in the second quadrant. So our vector looks something like that. Okay? So that means looking at line 1, everything in that direction above line 1 are going to give me values, because remember it gives you the increasing values. So it's going to give you values that are greater than or equal to 7. Greater than or equal to 7. Okay? My feasible region, however, is not on that side. It's not on that side of the line. My feasible region is on the other side. So I know that since my feasible region is not on the side that the gradient vector points into, okay, that means that the values that I want are when the numbers for L1 are less than or equal to 7, right? So I want everything less than or equal to 7. Because if I have greater than or equal to 7, I'm going to be pointing in the direction of the gradient vector, which is what I don't want, because my feasible region is not on that side. Okay, so if I go back to this these equations that I drew, I'll just erase the equal sign and write in what the individual signs would be. So for this first equation, again, I'm not shading in the direction of the gradient because my feasible region is not on that side. So I'm not going to be putting greater than or equal to for this first inequality. I'm going to be putting less than or equal to. And remember, I'm putting in equal to because I have solid lines. Now, for the second line. The second line, I'm going to, I'll put that vector in a different color. So for the second line, that gradient vector is -3, 8. So that gradient vector actually looks pretty much the same as the previous gradient vector we drew, so I'm not going to erase it. But I'm going to be looking at line 2 though. So if you look at line 2, notice that the feasible region is on the same side that the vector is pointing in going from line 2, right? So that means for my feasible region, I'm going to need greater than or equal to values for my feasible region. So I'm going to write greater than or equal to for that symbol. Excuse me, for that inequality. Okay, and that should make sense. Okay, so those values are going to be greater than or equal to. Now, similarly, if you do this for line 3, Line 3, you, again, are looking at the gradient vector. What is the gradient vector? The gradient vector is 1, 2. So that gradient vector is in the first quadrant, looks like this. Okay, that means for L3, okay, so for that third line, the greater than or equal to values are going to be on the right side of that line. But our feasible region is not on the right side, it's on the other side. So we're going to need less than or equal to for this inequality. Okay? I hope that made sense. So now we do actually have a system of inequalities, okay, that defines this feasible region. And if you wanted to check to see that, you know, what we did is true, you can easily use, and I see my battery's low, but you can easily use the test point method to just verify. I mean, I can prove to you at some point that this is true, but if you want to use the test point method to verify, you can. And you can see for the first line, 0, 0 is on the same side as our feasible region. So if you plug in 0, 0, you should get a true statement for the first line. And indeed you do. If you plug in 0, 0, you get negative 2 times 0 plus 3 times 0, which gives you 0 for the left-hand side. So you get 0 less than or equal to 7. So you get 0 less than or equal to 7, which is true. If you go to the second line and you plug in 0, 0, notice for the second line, 0, 0 is not on the same side as the feasible region. So since it's not on the same side as the feasible region, that means that 0, 0 should give us a false statement when we plug it into the inequality. And if we plug 0, 0 in here, we get that negative 3 times 0 plus 8 times 0 is greater than or equal to 7. So you get 0 is greater than or equal to 7, which is not true, which is what we know we should get. Okay? And then if you go to your last inequality and you plug in 0, 0, you will see that that gives you an affirmative statement. Okay, that gives you a true statement. Why does it give you a true statement? Because 0, 0 is on the same side of the third line as the feasible region. So here you get 0 less than or equal to 7, which is true. Okay, so you see it works. So in sum, our feasible region is, our system of inequalities is simply minus 2x plus 3y less than or equal to 7, negative 3x plus 8y greater than or equal to 7, and x plus 2y less than or equal to 7. And that will give us the proper feasible region. I hope this helps. See you next time.